In this video, we'll give you a rough overview of the output capability of CoolSim. This is actually CoolSim version 5 I'm using here, so this is a new version, and we've got a couple new features here. When you get ready to do post-processing, you go to this plot setup section right here. I'm going to show you a couple of variations. The first one is the base report. This is the menu that pops open. You can grab this and stretch it. You see right here I have nothing turned on. So this is going to show you the base model just exactly as it comes out without doing anything. You don't even have to visit this panel if you don't want to. When you submit the job, it processes on the host and it gives you a series of emails. I'm going to show you those. The first email it gives you is the start email. I'm going to bring my emailer over here. It gives you an email that says the process has started on the remote simulation facility. Now this is coming from no reply at CoolSim, so it's very easy to make a rule, and I have made a rule here in my Outlook that says all emails from this source go to a folder called RSF notifications. So the first one right here is the model has started. The next one you will get is that the model has finished. The model is successfully completed. There's two things here. One of them is the start time and the stop time. So you can see here that my model started at 2021 and ended at 1952. So that means that it was fairly quick. I'm sorry, it started at 1952 and ended at 2021. So that model took 21 plus 8 minutes, 29 minutes, about 30 minutes to run this model. And it comes with a full output report here in PDF. I'll show you that in a moment, but first let me show you that you get this email that says your job started and completed. So let's go take a look at the report. The standard report is here. Under the lower left-hand corner you have reports. You have the design tab, which is the input model, and then the reports tab, which is the output model. This will come back to you as soon as the job is done. It will be downloaded using this status report button. If the model's not complete, it will show you the progress. I'll show you that in a moment. If it is completed and you select this, it will simply open the same report. The report is characterized in two broad groupings. The first here are all numerical data. So here we have a description of the data center, how it was run, the number of cores it was used, the dimensions of the data center, the number of cooling units, the flow through it, heat removed, total number of racks, all the information that you would want about this data center is shown here. There's also an energy report. This energy report can, as I have done here, put in some values, can determine the cost to run the data center. It also gives you these parameters, RTI and RCI. These are taught in the Data Center Energy Practitioners Organization group that is part of the DOE's certification for energy managers. You see here this number is very low. These three numbers should be, for an optimal design, right around 100. If this one is low, that means we're delivering more air than we really need. So in the numerator you have here, this is a ratio of the total amount of air demanded by the racks compared to the denominator, which is total air supplied by the air handlers. You'll see up here that I'm supplying more than I need. Total flow coming out is 115. The total required is 98. So that's less than 100% because this is in the denominator, this one's in the numerator. That's how you get your 79%. So we're oversupplying air. This one is hotspots, RCI high. Do we have any hotspots? No. But RCI low is negative, which means we're too cold. We're supplying air at just way too low a temperature. That negatively affects the efficiency of the cooling system and the cost. Down here we supply one plot just in this section. This is the conformance plot, and you can see it's below. It's actually failing here. I've got this set for Fahrenheit. It's actually failing on the low side. So the ASHRAE spec for acceptable inlet conditions is 64.4 to 80.6 in Fahrenheit. If you're below 64.4, it's actually going to fail. in the report because it's below the recommended inlet temp. It's too cold. You can see it there in blue. Green means it's in. If there are any red spots above 80.6, it would show as red. We get down here to the rack cooling report, and you can see that it is failing. This would both be green if it were healthy. It's not. It's too cold. And you can see here that the rack inlet temps, the minimum is below that spec of 64.4. So we give you the min, the max, and the average. And we also give you the average exit temp, the flow rate, and the amount of power in kilowatts for each one of those racks. And we do it for every rack in the system, all the way down. You can see most of these are too cold. None of them are really passing. In green, we give you the coldest one. So this is the coldest rack. That's the lowest. And in red, we give you the highest one. Even in the red case, we're still at 62.1. We're too cold. So this is not unusual that we see a data center with simply supply air temps that are too cold. That robs it of energy. So that's the rack report. For every object in the room, we do a report. So here are all the tiles. Most of them are 25% open tiles with the flow rate and the variance here over on the right, deviation from the mean value of the flow rate. See quite a bit of variation here. Again, we give you the highest output, and we also highlight the lowest output, 448 in this case. Almost 40% below the mean. We'll get into why in a moment. CRAC Performance is the next one. This one gives you, for each one of the cooling units, it gives you the return temp, the supply temp, the flow rate, static pressure. This is external static pressure. This is the top and the bottom of the cooling unit itself. They're looking at the delta P across it. This happens to be in inches of water because that's how I ran it. You can choose any metric you want. Europe would be pascals, of course. Total heat removed. This is the total heat removed. And you'll notice there's one of them here in red. This means that it's exceeding the nominal specification for that unit. So number 45 is operating with a delta T here in a heat rejection that exceeds its capacity. So return temp is 77 degrees, supply temp 56 roughly, and that's a problem. So when you see red here, what it means is that you are exceeding the capacity, the nominal capacity of that unit, and you have to do a little more investigation to determine whether that's going to be successful or not by looking at the specifications for that unit more closely. Okay, so these are all the numerical outputs over here on the right. On the left, we have all the 3D outputs. So here is a full set of 3D images. Up here at the top, we have just a 3D representation of the shaded image. So this is just a representation of the room itself. These are independent windows that can be stretched and can be manipulated. We have keystrokes on this, so the most obvious are X, Y, and Z. And there's also N is the perspective button, so you can turn off perspective. There's also, you can do capitals on these too. So capital X, so here's X, here's capital X, Y. Capital Y will shift it around the other way, and Z. And capital Z. So you can use capitals to flip it the other way. That's upside down. That doesn't really help us, but that's how it works. If you want to see through a block, so you want to see what's going on, we can do that too. This is part of Ansys technology. Right up here there's a view manager, and in the view manager you can select to eliminate surfaces so that you can see through the model, and then you can simply close that. At any point you can print an image of this. The image will come out in the exact orientation and size of the window. So as you change the size of the window, you change the aspect ratio. A simple P key, P, the letter P, will allow you to write out any image that we see in the CoolSim output. So great for producing PNG images. These things are true for all images I'm going to show you. I happen to be showing you geometry right now. The mesh is shown here. This is just surface mesh. If you're interested in seeing it, one of the interesting things about CoolSim is its meshing technology. It's from Ansys, of course, and you'll notice we're body fitted. So in most systems you'll see in this market space, you'll see Cartesian stair-stepping around this. Here in our system, however, it's body fitted. We use a non-uniform hybrid body fitted mesh. Very advanced technology, very nice technology. You notice I'm using hex dominant out here for those of you who understand meshing, hex dominance out here gives you better resolution for perpendicular flows with fewer cells, but as you get close to a round surface, you really need to do something. So we transform into a different kind of mesh. You can see here we can produce tetrahedras if we need to get up against these edges. Very nice piece of technology. So there's the mesh. Now down here are the most important things. This one is the recommended range for rack inlet temperature right here. So you see this is conformance. This is a conformance plot. It's kind of a go, no-go kind of plot that and again you can size this window any way you want. But here we're looking at rack inlet temperatures, and you can see they are below, most of them are well below the recommended inlet temp for racks. Now this won't hurt a rack. It's not like you're going to damage the IT equipment running this cold, but it certainly is an energy problem. It doesn't help you on the energy side or equipment side to be running at such low temperatures. And we also give you the full range temperature here too if you want. So this is the full range. What we do here is we take the maximum and minimum values seen in the flow field. So this flow field is running, the complete flow in this environment is running at a high of 80.9. It's the highest temp seen up here in these edges. The lowest is 52, and we simply take color and spread it out over that range. And that's how this plot works. And then we have the allowable range. Now allowable is a little broader. This is the ASHRAE allowable range. And again, I'll just stretch these windows so we can see them. You see there's more green here and less blue. So we've got more racks passing. We're still below the allowable range. We're still too cold. And you'll see in the cooling report that we're throwing air at a very cold temperature here. So I can just go back over to my numerics, get out of tile rows here and go back and look at my cooling units. And you can see I'm supplying air here at awfully cold temperatures. This is not really something you want to do, but in this case we did it for purposes of demonstration. So back over to our 3D, we now also have, we did the rack ranges. Now what CoolSim does automatically is it puts 3 cut planes or contour planes in each section, X and Z. It puts 2 of them in Y. So let's do the first one. This is a temperature plane. We just slice the room into thirds, 1, 2, 3, and put a temperature plane in here. In other words, we don't know exactly what you want as a user for your planes. Where do you want these planes to be positioned? So we simply take the room, cut it into thirds, and place them in different sections of the room. So this is the center section, and then we'll have the lower section in Z. The axes is always shown. Y in CoolSim is straight up. Z is planar, and X is planar. So X and Z serve the 2D plane. That's this plane. And then Y is the vertical. Now you can change these. You don't have to have them here. You can put them anywhere you want. I'm going to show you how to do that in a moment. But let me just walk back through it. Here's your pressure at minus 0.75. This is a mid-plane, what we call a mid-plane cut. We cut in the raised floor data center. We'll take the mid-plane. We'll go right to the middle of the floor. You can see there it's pretty much right dead center in the middle. And we'll do a pressure plot, just to show you the pressure variation under the floor. Again, what we do here, and I can stretch this out, what we do here is we look at the max and the min values of pressure under that floor as compared to room average pressure, and we plot it. And the reason these are cut out is because there are underfloor cable trays on this design that are blocking. So you can't see any pressure there because it's right straight through them. So there's a pressure plot. We also have a very nice image here. This is Flowrate on tiles. This particular one takes a little bit of time to load. By the way, these results are all now local. Once you download them from the cluster, they're all local. So I'm just manipulating them locally on my local computer. And here we see the, oops, where'd it go? This is the image on that output. I'm just going to stretch it a little bit so we see it. So here's and this is kind of an interesting one. The best way to look at it is from the top. So I'm going to use my Y key to orient it. I'm going to turn off perspective using my N key. And that's a very nice shot right there of the variation in air coming out of those floor tiles. You see here in the center, we're at about 948 cubic feet per minute per tile. We're near an edge. Over here, we're at 488. So that's a variation of almost 2 times, and it's caused by underfloor pressure and underfloor velocity. In particular, these cooling units that are on the edge over here are very close, and the velocity underneath the floor here will cause these to have trouble in flow rate. They sometimes will actually go negative. I've seen these numbers go negative because it's pulling the air into the floor instead of pushing the air out of the floor. Anytime you get close to a cooling unit with underfloor cooling, you're going to run into that problem. So there's your flow rate out of tiles. And then we have Pathline Plots. I find these to be very useful in terms of understanding where the flow is coming from. We do separate them just for clarity. Instead of sticking them all together in the room, we do it in 3 sections. We show you path lines from cooling units first. So this is the path lines coming from the cooling units underneath. This is one of the path line images. This is from tiles. So we're looking at the path line coming out of the tiles here. And you see a couple of things going on. In this image, we're seeing some short circuiting. You don't want to see that. This is air coming out of the perforated tiles up and over the top and right back to the cooling unit. So it hasn't gone through the rack. It's just coming out of the area where the cold air is coming from the tiles and moving right straight back. That's a problem. Now, we're supplying too much air. We already knew that. This cools off the return air temps and causes the delta T on these racks to be low, on these cooling units to be low. And the result of that is poor performance. Now, over here we might want to get a look at the data center from this side, and this is blocking us. So again, we use our tool in the upper left-hand corner. I'm going to shrink this a bit so you can see it. I'm going to put this up like this and stretch it so you can see what I'm doing. In this upper left-hand corner, there's a view manager. And in that view manager, if you click on this little caret, it will show you all the surfaces, and you can turn off surfaces so you can see what's going on. That's very handy because now we can see through blocks. We can also do it for racks as well. If I wanted to see the path line coming out of the tiles behind these racks, we can also turn off the racks themselves. So let's turn off the rack. And what we see here is, as I mentioned to you earlier, these cooling units are very close to these tiles. You can see the Bernoulli effect right there. Air coming from under these tiles. I'm only showing you the path lines coming out of the tiles. But you can see what's happening there is as they come out, they continue to move because they have momentum. And that momentum wants to continue to move them. They're running at very high velocity under this floor. This is a fairly shallow floor. So the air velocity is moving under this floor very quickly and wants to continue in that direction. And so there's not a lot of pressure here. Remember that pressure is the total of static plus dynamic, and they trade off with one another. So as the dynamic pressure is high here, the static pressure is going to be low. And that's why I'm having poor performance in this section. I have hot spots, if you remember, up in this top of this rack, because there's no air coming out of this tile because the underfloor velocity is too high. And that's a very good shot of it. Furthermore, it's getting feedback or coming back to the cooling unit itself and short-circuiting. We have short-circuiting going on over here on this one as well. And so there's quite a bit of recirculation going on, causing problems. If you wanted to make a shot of that again, if that particular image was interesting to you, you would set the size of this window to be whatever aspect ratio you want it to be. You can just stretch it to whatever you want. Select the P key for print, and it will ask you where you want to save it, and you can save it off using the file manager and put it in your directory anywhere you like. Just put it on my desktop and write it out as a PNG file, and that would be fine. So, yep. So that's it. That's the base ones. Now, to modify post, you don't have to go back through that whole sequence. In other words, you can simply resubmit the job for post. So let's compress these back down. Let's close some of these sections here, and we're back to the base report. If I wanted to change something, for example, I wanted to add a cut plane, or I wanted to change the position, or I wanted to change the range, you can do that right here in Plot Setup. And the way you do it is to just hit Plot Setup, go in here and flip this switch called Modify Post. Now, Post stands for Post Processing. Stretch this out so you can see it. We can turn on velocity contours, we can turn on some animations, we can turn on clouds. These are all options. You can also, for any one of these groupings, you can add up to 10 cut planes or contour planes. So if I wanted a contour on, let's say, the z-axis in a different location than what I have it, I can go find out. I can put one in, and if I need to know where it is, if I want to know where that cut plane is, I can just slide this to the side and move my cursor in here, and down here on the bottom it will start to record where my cursor is. So here, and I can see from my axis that Z is in this direction. So let's say I wanted a plane somewhere in this region. I could look down and see that my Z is at just about 48.6268, and X is at 71. I'm interested in a Z plane at this case, so I would do 47, roughly 47 feet, so I'd add a Z plane at 47 feet. So we allow you to use the cursor to determine where you are in the room so that you can add contour planes. Same thing with velocity. If we wanted to look at velocity over near, and you can just move this out of the way, over near this section where I was showing you where I know we have high velocity, I'd like a plane in this direction. That would be the plane in the Z plane, and in terms of location, looks like about 4 feet would do it. So I want a velocity plane in Z at about 4 feet in. For CoolSim, it's important to remember that the axes, if you put this into top view, CoolSim 00 point is the upper left hand corner. So the coordinate system sits in the upper left hand corner, and that's where you measure from in the model. So let's go back and look at a couple more things in plot. Contours we can do here. We can change the scale of min-max temperature, we can change pressure. So if you wanted to limit your scale, you can flip this off and just set these to be whatever you want. Number of path lines, we can run high, medium, or low. Okay, so you can put those in anywhere you want, and you don't have to rerun the entire model to do that. If you've run the model fairly recently, at least within the five most recent working days, calendar days, then you can simply, when you hit the run button, instead of rerunning the entire model, you can rerun post only. One other thing we've just added in version 5 that I want to show you is this results available by hyperlink. If you want to share any of these results with someone else, just flip this switch and it will generate a hyperlink for you that will come to you by email. So let's submit that job. This will run very quick because all I'm doing is, and you want to choose yes here. When rerunning, please don't change any input parameters, just output parameters for post only. Yes, you answer yes to that. It will go and start to process for you a new job. This is quite quick. It handshakes with the cluster, passes the revised model. The full set of results is still sitting on the cluster. You can use the status bar to kind of keep track of your job. And you can see here that it's doing a countdown. Every minute it will take a look at that cluster to determine if it's ready to come back or not, or what the status is. This is the same when you run a full job, you'll get this sequence. But here, because we've already done the results, as soon as it's ready and we check it the next time, it's going to drop all the way down into graphics generation generate graphics and report generation, and then download the output. So that's how that works. And while that's processing, I'm going to show you some of the emails you get from the system. So when the job is done, as I mentioned, you'll get an email that says your job is finished. It will tell you the start and stop time. So this is how long the job took to run. You will also get a full PDF output here that's an attachment. This is a customer deliverable if you want, and it's a full PDF. And what we've done here is expanded every section. We've added in the most important plot, which is the ASHRAE Recommended Plot, and here we've set all of them to be wide open so that you can take a look at all the parameters that are being generated, all the alphanumerics. This comes as an attachment to the email, so be aware of that. That's why having your email is important, so we can send you these. And then the other thing that's important, when you flip that switch, like I showed you, it generates for you a hyperlink. And this hyperlink will allow you to open the entire report using a URL. So here you see the URL. We're using Amazon to post this. So you can view this and share these results with anyone. So I can open one of these, like this particular contour plane. I can take this URL, I can copy it, and I can paste it into an email. I can hide it behind a 2D image. I can put it into a chat box. I can send it to somebody using text messaging and be able to share this image. They'll be able to view it anywhere, including their phone if you'd like. So this is a new feature that we've just added. We think it's going to be very powerful because now you'll be able to use documents of any kind, Word or PDF or PowerPoint, and behind each one of your images you'll be able to put the hyperlink, the respective hyperlink as shown here for that particular image, and they'll be able to click on the image and show it in full 3D. So just to show you how to do this while that other job is processing, I'm going to print this particular image. I'm going to write it out to my desktop. My desktop looks like it's got a problem, so I'll just write it out to this directory, thermal management. Now I can open, and I'm going to take the hyperlink as well. So there's the hyperlink. Now I'm going to be able to then open Word and use this in a Word document. So let me go here to Programs and open Microsoft Word, if I can find it quickly. And so now I'll just do a blank document. My point here is I can put text in. I can then insert that image. So here's my image. I'm going to go to Pictures from this device, go to Thermal Management, and grab that picture that I just put in there. So there's my little image. Okay, I can center it just to make it look good. Put a caption underneath it, maybe. And behind this image now, I can insert a hyperlink. So here's my link. Control V, put this in, and now that image is linked. So I can continue to, write anything I want, continue to go forward, creating this report, and I can save it off as a Word doc, or I can save it off as a PDF. And if I save it, for example, as a PDF on this machine, in the same location, I'll put it in Docs. I can make it Test, save it as a PDF. The user will be able to open that and view the 3D. So let's just close this for a moment. I don't want to save it. Let's go over to my File Manager and grab that document. So we're going to go here to File Manager and go to my Docs under User and grab that image, that document. So see Users, Me, Documents, right there is Test PDF. Now this is a PDF. So you see here it's a PDF. I'm using Acrobat to open it. But when I go to this image and I click on it, I get the full 3D output. That's pretty interesting. I think that'll help you all a lot in terms of bringing full 3D life to your customer. Now let's go back to CoolSim. You see here the CoolSim is now, it's already dropped all the way through here because it did not have to redo the mesh. It did not have to redo equations. All it had to do was generate graphics and output a report. And so in the next phase here, it'll download a brand new report complete with everything based on the additional parameters that I set for it. So that's a pretty interesting way to do this kind of work. This avoids having to have the full set of results local. The set of results are on the cluster, and what we're doing is rerunning a script on those sets of results to process a new complete output. When the output is done, it is downloaded to the machine just like it was before, and you see here now the report is coming down. So while this demo was going on, I completely redid the entire set of results for this model, adding in cut planes or ranges or what have you. It will not vary in speed depending on what you do. It doesn't matter. You can change it all you want. It doesn't really impact the speed much at all. So here it's downloading a new report, and the download is fairly quick, and will display for you when it's done the model with a complete new set of output based on the updated parameters that you provided to it. So here we have, just like we saw before, but the extra planes that we put in are now available. And so here's some of the velocity planes that I put in place. Remember, I put a velocity plane of z at 4 feet so we could see the high velocity coming out of the bottom of those units, and you see there they're shooting out at 1200 feet per minute out of the bottom of those units. So that's extremely high, and that's what's causing the issue with the underfloor. Likewise, we generated some animations this time. So we can see animations in X, Y, and Z. We can see temperature clouds if we want. So there are some extra features here. Furthermore, CoolSim allows you to do some settings. If you want to change units in the output report, you can do it right from the settings parameter here, down at the bottom under settings. So if I wanted to change my cooling capacity for some reason to tons of cooling, I could change it to tons, and it would change in my output report. So when I close it now and I go back to my performance report, I'm going to see output in tons. So it does allow dynamics. It doesn't do it on the images. The images are still going to be fixed, but at least it'll do it for the report itself. So that's a quick overview of CoolSim's output capability. It's quite significant. This new hyperlink feature that's in version 5, I think you'll find to be extremely nice, and the images on this system now are really quite good. Animation sequences aren't too bad. They're a little coarse. We'll upgrade those soon, sometime in the future. We also have path lines from the CRAC units. This is an overhead shot. We have path lines from the racks themselves, path lines from tiles. These are all animation sequences that you can download, and yep, temperature clouds. These are isothermal clouds of temperature. But that's a quick overview of the CoolSim post-processing capabilities. Quite extensive, and now something that you can share very easily with colleagues. Thank you.